Good afternoon, everyone. Welcome to the Inter-University Center for Astronomy and Astrophysics' yearly celebration of the Pulastya Science Festival. So we are here online this year with several educational as well as very fun activities today and tomorrow. Bringing to you all these things online this year because of these strange times when we are confined to our homes. And we wish all of you could have been here at IUCAA and enjoyed these activities with us in person. We've been doing this for over a decade now, and this celebration is centered around the birth anniversary of Sri Pula Deshpande. So Purushottam Deshpande is a prolific Marathi writer. He has been, he was with us and he is a great friend. He was a great friend of Professor Jayan Narlikar, our founder director. However, after his passing away, we had to Science Center. People can visit it on any weekday. But right now we are all confined, constrained, and we are missing all the visitors who come here and make our day. So to celebrate this occasion, we have today and tomorrow a lot of events lined up, including some talks, some interactions, and some fun activities that you could do at home as well. So with a broad range of attendance, including students, their parents, and general public who are just interested in astronomy, let's go ahead with the starting of the Pulastya Science Festival this year. So to begin with, I will invite Professor Shomak Rai Chaudhary to please say something about IUCAA's outreach and his feelings about this festival.
Good afternoon. My name is Shomak Rai Chaudhary. I'm very, very happy to start off yet another year's celebration of the Pulastya Science Festival. We look forward to this event all year because our association with science popularization and science outreach, even though IUCAA remains a pedagogic institute with research and teaching being the main mandate of IUCAA, interaction with the universities, right from the very beginning, with the vision of our founder director, Professor Jayan Narlikar, more than 30 years ago, now 32 years ago, from engaged with the general public, with schools, school teachers, school students, and and the amateur astronomers in the country. All that started very early on campus. We've had interaction with the public and with schools right all the way back from 1993. And during that time, we at Pula Deshpande, of course, then very much alive and very much the premier writer in the Marathi language, would visit IUCAA. I remember in those days meeting him, and he expressed a lot of interest in science, not only through his friendship with Professor Jayan Narlikar, but also in the activities that IUCAA had started with engaging with the general public. He really appreciated it. And as a result, of course, he and his wife, Sunita Tai, both got engaged in our activities. He left us some donation when he passed away, which resulted in our building a lot of our science popularization infrastructure. As Samir mentioned, the Muktangan building, and then of course it started working as the hub for our activities in the science center. We associate Pula's interest in science as also something that is one of these ideal things that don't happen as often as we want. The interaction between scientists, mainstream scientists, and mainstream people from the arts and literature. And there are some rare cases which stand out in the history of science. We have great examples of, for example, Milton interacting with Galileo, of J.C. Bose interacting with Rabindranath Tagore. And this is an amazing case in which Pula got inspiration from his interaction with Professor Narlikar, and vice versa, I would think, because Jayant Narlikar is also a prolific writer of fiction in Marathi, with the characteristic humor in it, which was very similar to the humor that you get in Pula's writings. And so we decided many years ago that we would start this festival in Pula's honor to celebrate not only his association with IUCAA, but his association with science, and in particular astronomy. And so from the very beginning, we've had this connection with not just the general public, but we've made a huge effort to interact with the artists, the theater community in Pune, the music community in Pune, and slowly that has now increased. If you look at the various programs we have in IUCAA, other than our scientific activities, you will see a lot of interaction with the arts. And it all started with our interaction with Pula. And I think, and then of course, the Pune has a very thriving community of writers and actors and the stage, as well as and literature in all forms, art in all forms, music and dance. And this we try to celebrate in our activities, and we also are looking for new ways of producing or interacting with the artist community and the literature community. We recently celebrated Pula's centenary year last year, and from that time there's been an increased awareness of his writings, and there have been various translations, productions, etc., of his plays and things like that, and that also gives us another opportunity to highlight what we are doing here. And from the very beginning, I've been associated with IUCAA's outreach program. And increasingly, we have seen a lot more interest, not from just the general public, but this community of creative people who see IUCAA's our work here as a research in astronomy, which is also very, very creative, and the underlying creativity of both the artist community and the scientist community can actually come together. And this message is something that we want to give. It's a very unique occasion during the year. We have various times when we have zero shadow day, when we have solar eclipses, and we have comets, and we have asteroids, and meteor showers, and all kinds of things. But very rare occasions where we can celebrate the coming together of the science and the arts. And that is very, very important. It also, today, as you know, is today, I think, is the birthday of C.V. Raman, right? As well as Marie Curie. So two very, very important figures. And so you can see that it's a very auspicious day for us starting off such a program. So we have also in this series of programs that we have around Pula's birthday, and this Pulastya Science Festival, we emphasize activities in various languages, particularly Marathi, because of course Pula was a writer in this particular in Marathi, but we see also Pula as a national figure, and so we have programs in Hindi and English altogether. There are quite a lot of interactive programs. There will be some recorded programs today. We have also incorporated a very important program this evening, which is being held by the LIGO India outreach group, which is an interactive session with Rainer Weiss, Ray Weiss, who's a Nobel laureate for LIGO 3 years ago. And we've incorporated that as part of our celebrations, because he expressed an interest in interacting with young people. And so there will be a very important session, which is quite consistent with what we do. Today is also the 8th anniversary of Sunita Tai, and so it's as I said, I mean, we are celebrating associations with lots of figures. After Pula Deshpande's passing away, For her remaining years of her life, Sunita Tai was very intimately connected with IUCAA. She visited us many times. We have trees planted by her, and she had an active interest in the functioning of IUCAA and IUCAA Science Popularization Program. With these initial words, I would like to start off the program, which goes on for the rest of today till evening, and also tomorrow. And tomorrow the programs are in Marathi. Today, let's start off, and I'll hand you back to Samir to start off today's program. Thank you.
Thank you very much for your kind introductory words, Professor Raichaudhuri. Yes, we are celebrating Pula Deshpande and in fact the whole family, because we also today mark the death anniversary of Sunita Tai Deshpande. As Professor Raichaudhuri said, that we had a long association, and I personally remember having seen Pula and in fact joining astronomy because of Professor Nalika. So this connection is an amazing coincidence that finally I get to work at a place which is part of both their visions. And of course, Sunita Tai Deshpande was a mentor for many more years, and we remember her today. Last year, we celebrated 100 years for Shri Pula Deshpande, and he's still fresh in our memories. And as you might have noticed, I still think that he's there with us, and we keep listening to his recordings, and we keep reading his books, and we never kind of get over the humor. It's always there, and it always makes you fresh. Another thing which makes us fresh is indulging in science experiments. And that is what we are here to enjoy today. So, of course, as I said, the coronavirus has kind of confined us, and in schools, etc., are working online. Of course, online is sometimes boring, but there's never a boring moment at the IUCAA Science Center, at the Muktangan Vignan Shodhika, which is, as the name suggests, is an open place to explore science. So we always bring to you great edutainment. And today we carry on with the same series. And we have the team working here, which is the MBS team, the IUCAA Sci-Pop team. And we have, let me just mention them quickly. We have Rupesh Lavde, we have Shivani Pethe, Sonal Thorve, we have Ishan Shinde, Atharva Pathak, and Tushar Purohit, all working at various places, either from their homes or from their office. And we have Professor Surud More also present in the background, who will again join us tomorrow for a lot of interaction. So other than that, we also have the contribution from several researchers at IUCAA. So they will come on later live and answer some questions which some of you have asked over the past few days. So all this is lined up, and as Professor Raichaudhuri said, I'll point you to the fact that we also have a Nobel Prize winner speaking to us, speaking to the younger generation in his own characteristic, fun way. Well, he, as you will know, has won the Nobel Prize for the discovery of the gravitational waves in 3 years back. So we will celebrate a special day, unique day, on which two Nobel Prize winners, two unique Nobel Prize winners were born. And that's a great coincidence. And we will have Professor Rainer Weiss also speaking to us in a very different kind of interview, a friendly, interactive interview. But that will be on the LIGO India live channel. So please, at the given time, please log into please shift to the LIGO India live channel to watch it. Don't miss it by any chance. We'll also, of course, be including the link in the description of this live telecast. So do keep a note of that, and don't miss it at any cost. So let's begin with the celebrations of today's event. And I have my colleague Sonal Thorve joining us, and she will enlist the activities. If you're not already aware of the schedule, she'll quickly tell us about the schedule. And I think she's also ready to do some activities with us. So over to Sonal, And all the best. Let's have fun celebrating this day. Thank you very much.
Thank you, Samrida, and thank you, Professor Rai Chaudhary. So I'll just enlist what all activities are planned for today. So to start with, we are going to have pre-recorded sessions as we had to perform the activities at different places. So there is first session on COVID awareness through science. So Shivani Pethe has recorded it, and we are going to view that. It has some wonderful demonstrations which you all can try at home. Then we are going to have a session on trending solar system. So as Professor Rai Chaudhary mentioned, there are many happening things in our solar system which have been on social media for this year. Then we'll go to the live session where our IUCAA research scholars are going to answer the questions live. That session will start from 4:15 onwards. After the live Q&A session with IUCAA academics, at 6:30, as Sami said, we are going to shift to the LIGO India YouTube channel. The link is mentioned in the description. Please visit that channel. The session will start at 6:30. As soon as the session or the beautiful conversation with Professor Rainer Weiss gets over, you all are requested to join here back on IUCAA SciPop's YouTube channel for a wonderful night sky watching live from telescope. So thank you very much. Let us start with the sessions.
Is coronavirus for today's demonstration. So, do you know how much tiny this virus is which is causing such huge disaster? The size of this virus is very small. It is approximately up to 0.1 micrometers. Yes, it is that small. And the bacteria, those are around 1 micrometers. And the human cells that these viruses and bacteria are damaging is 100 micrometers. All these numbers seem a little confusing. Let us compare them with something we know from our day-to-day lives. For example, a pin. Can you see the tip of this pin? So tiny, right? Consider this tip of the pin to be the virus. Then how much big is the bacteria? Around this much. And how much big is our human cell? Around this big. Yes, something this big is getting damaged by something this small. So, it is very important to Hello everyone. After the great introduction by Sir, let us start with our 20-minute demonstration of science. So this year has been a little unexpected because of the big and huge pandemic that we are suffering from, and we all are locked up in our homes and working from home, studying from home, attending the schools from home, and similarly watching all these videos. and attending these festivals like Pulastya from home. So I thought, why not pick up the same topic, that is coronavirus, for today's demonstration. So, do you know how much tiny this virus is which is causing such huge disaster? The size of this virus is very, very, very small. It is approximately up to 0.1 micrometers. Yes, it is that small. And the bacteria, those are around 1 micrometers. And the human cells that these viruses and bacteria are damaging is 100 micrometers. All these numbers seem a little confusing. Let us compare them with something we know from our day-to-day lives. For example, a pin. Can you see the tip of this pin? So tiny, right? Consider this tip of the pin to be the virus. Then how much big is the bacteria? Around this much.
आता त्यांनी कशावर काउंट केलं होतं?
Around this big.
Oh, okay.
Yes, something this big is getting damaged by something this small. So,
आता तुम्ही लेटेस्ट जी लिंक पाठवली होती त्याला जर आपण क्लिक करून परत एकदा केलं तर जॉइन होईल का ते? नाही होणार.
Why? What does soap
recurring
actually do? Let us try something fun, scientific with the experiments, the material that I have today. I have water, colors, milk, some pepper, black pepper, and some soap. So for the first experiment, what we are going to do is, I have taken a dish. I think we should take the camera a bit closer to the experiment so that we can see what actually is happening. And I am very thankful to my friend Poonam. She is helping me today with the camera. So now I am taking water in the dish. And this is black pepper that we use in our house every day. It is grinded. And see how it sits on the top layer of water. And do you know why this happens? This is happening because the surface tension of water is high. And now what I'm going to do is, I'm going to take a bit of soap and dip it in water. See? Fun, right? This is a very, very exciting experiment. I feel it very exciting and I'm sure you would love it. Please try it home. Just take a dish, water, and sprinkle some powdered pepper and a bit of soap. So what actually soap did? You know, water is a polar material and soap is something like this earbud. It has one end which is hydrophobic and the other end which is hydrophilic, and hence it breaks the surface tension, the polarness which is giving the surface tension to the water. It breaks it and the top layer molecules of water spread away, taking the pepper with themselves. So the next experiment is disappearing germs. So let us make some germs on a piece of paper. I'm going to draw random lines with different permanent markers. Make sure you use permanent markers and draw something like this. Can we get the camera a little closer? See, draw something like this. I have one already made and put it in a Ziploc bag. Okay. So now what I'm going to do is, I've taken a jar of water, a Ziploc bag and a piece of paper on which I've drawn some germs. So now I'm going to insert this bag inside this jar and let's see what happens. Can you see the germs from outside? Yes. Now we'll see if we can see the germs from inside. Can you see the germs have disappeared? Can you see? See? And now from outside, you can again see the germs. Isn't this interesting and exciting? You can do this at home, and the only reason behind this is refraction of light. Light bends in different mediums, that is air, water. It has different velocities, and so it travels with different velocities in different materials. It travels very fast in rarer mediums like air, and it travels slower, that is with less velocity in denser mediums like water. Please try it at home, and I hope you will like it. So now let's see some colorful germs going away from soap. For this we need a dish, some milk, some food colors and soap. Now let's get the camera a little bit closer to our experiment. And I'm pouring milk. I have some food colors here. And I'm dipping my earbud into soap and just keeping it in the middle. Can you see how the colors went apart? And you can see the reaction is still going on. Can you see the reaction still going on? The colors oozing out. So this was a really colorful and very exciting activity. Please try it at home again. And why is this happening? This is happening because, as I explained, the soap has two ends. One is hydrophobic, the other is hydrophilic, and hence it breaks the surface tension of water. And now here we have milk. So milk has two parts. One is water and the other is fats. So the fats that are in the milk are used up by this reaction, and hence the colors are also getting oozed out, and the water and the fats are getting separated because of soap in the milk. So these are some of the properties of that substance itself, which gives you the idea of the reaction. Now again, the science activities are over here, and we are going to go with some fun and some more colors now. Now I have two globes over here, and when we wash our hands, are we really washing the germs away from our hands? Now let's check. So I have some paint, and I'm going to take that paint on my hands. So imagine that this is our soap, and when we wash our hands like this under the water, see how much part is covered. All the germs inside your fingers and at the back are still remaining. So what we need to do is, we need to cover our hands from the back side also, and in the middle of our fingers like this very properly. Okay. So now when we do all this and cover all our hands, the germs from our entire hands are going to be washed away. And I hope you all are washing your hands, taking care of yourselves, your families, and be safe at home. And please don't go outside if it is not necessary. So I hope you loved all the activities and you will do all this at home. And now let's do another small 1 minute activity. It's not even an activity, it's a card. And you can do this at home, and 2 to 3 years old kids can play. So what I've done is I've taken a card sheet paper and drawn a tap with water, running water like this. And I've drawn a small kid's hands on another paper. So these should be of the size such that you make a slit in the water and this paper exactly fits into this water slit. Okay. Now let's bring the camera near and I'll show you how to play with it. I've also drawn some cute little germs here. So you can tell a story that when you come home, your hands are all covered with such germs, and if you wash your hands nicely with water, see, all these germs are washed away. Hey! I hope you loved all these activities and demonstrations, and let's move on to our next demonstration.
I hope you have all have learned why we need to wash our hands. And Shivani, those were very beautiful and fun activities. I hope you all can try these at home and enjoy. Those germs were really cute, but we all need to wash those germs away. So keep washing your hands. And let us now move forward to our next session, in which we are going to learn some things, some fun facts about the space.
Hello everyone, I am Sonal, and today I am going to tell you some exciting things about space. I am sure that when I said exciting things, you must have thought about black holes. But of course, we are not going to talk about black holes. We are going to learn about black holes and the discoveries leading to Nobel Prize 2020 by renowned astrophysicists themselves in our evening public talks in Pulastya Science Festival. So, we are going to talk about our closest neighborhood. Yes, that's our solar system. For decades, humans have been exploring space using advanced technologies. We started by sending space probes into the space to explore the space and celestial objects in it. Yet, the farthest of the direct physical reach of humans has been the closest of the celestial neighbors of us, the moon. Not more than 2 weeks ago, NASA's observatory SOFIA discovered water on the sunlit surface of the moon. 3 weeks ago, NASA's spacecraft OSIRIS-REx succeeded in collecting sample material from an asteroid named Bennu from the asteroid belt. The sample return capsule is going to return to the Earth in 2023. Talking about asteroids, young IIT students Kunal Deshmukh and Kriti Sharma, along with Chen Yen Su from Taiwan, detected an asteroid that flew past Earth on August 16th. This asteroid is not bigger than 6 meters in size, but it was the one which flew past us from the closest ever known distance. On September 14th, using the data collected from James Clerk Maxwell Telescope and Atacama Large Millimeter Array, a team of scientists discovered gas named phosphine in the atmosphere of Venus. On Earth, we know that there are some microbes which produce phosphine gas. This made the whole world turn its eyes towards this planet, which was once considered to be impossible to be a habitable one. In mid-July, skygazers across the globe were obsessed with spotting a comet, Neowise, that had travelled for almost 3,000 years to visit the Sun in its 6,800 years long orbit. The annular solar eclipse on June 21st was visible from some of the parts of northern India. Almost 98% of the Sun was covered by the disk of Moon. So, to summarize, it won't be wrong to say that the solar system bodies have rocked the year 2020. In between 1966, when Soviet Union's Venera 3 crash landed on the planet Venus, becoming the first ever space probe to touch another planet, and the OSIRIS-REx in 2020 touching the surface of an asteroid Bennu. Humans have sent many space probes, rovers, that have been orbiting different interplanetary bodies, that have been walked on the surfaces of different planets, moons, asteroids as well as comets in our solar system. All these adventurous expeditions of humans are the results of unending curiosity of us, as well as the thirst of understanding our universe better. And all these explorations are based upon the observations those dates back to thousands of years of the human history. Now, let me tell you a story of observational history of our solar system. Look up. When we look at the sky, we see the Sun rises in the east, travels a semicircular path around us and sets in the west in the evening. It returns back to the east again after about an equal interval of time. This suggests that the Sun must be going other half of the circle beneath us. Doesn't the Moon follow the same thing? And what about sphere of the stars we see at night? All of these things can lead us to think that the Earth is center of the universe and the Sun, the Moon, the stars are going around us. It was not long ago when people used to believe that the Earth is the center of the then known universe. About 2300 years ago came Aristarchus of Samos. He put forward a model of the universe in which Sun was at the center and Earth along with other planets is going around the Sun. However, 400 years later came Ptolemy. He refined the geocentric model of the universe. The belief remained for a longer period of time. About 18 centuries later, Nicholas Copernicus in 1543 came up with a model that was similar to the Aristarchus model of the universe. This was the Copernican model of our universe, or the heliocentric model of our solar system. This was the beginning of scientific revolution. Now, when we look up and see that the Sun is going around us or the stars are going around us, we know that it is the Earth that is rotating from west to east, causing the Sun or the stars rising from east and setting to the west. This is similar to something what happens when we are riding in a vehicle. Like the trees in our surroundings appear to go behind us in the backward direction while we go forward. So, the earth is our ride. Tycho Brahe was considered to be one of the best observational astronomers. He had collected a lot of data about planetary motions. He was probably the last astronomer who had observed the celestial bodies and collected a huge data without the aid of telescope. After Tycho's death, Kepler, who assisted Tycho in his astronomical observations, analyzed the data collected by him. And Kepler came up with the mathematical interpretation of planetary motions, now known as Kepler's laws of motion. Around the same time, Galileo Galilei was observing the planets and other celestial bodies using the equipment he had made, the telescope, that magnified the objects in the sky. In 1632, Galileo published a book in which he had stated that Copernican system or Copernican model of the universe, the heliocentric one, was correct. While planets were getting so much attention, Edmund Halley had observed a visitor in the sky in 1682. Using Newton's laws of motion and Kepler's laws of planetary motion, Halley predicted that this object will return again in the skies. As he predicted, the object was supposed to return in the skies in 1758. That object returned the skies in 1758 as predicted by Halley. However, he wasn't alive to see it. This object we know as Halley's Comet. It visited us last time in 1986 and it will visit us again in 2061. What are these Kepler's laws of planetary motion? Let us see. The first law says the orbit of a planet is an ellipse with the Sun at one of the two foci. The second law states a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. The third law states the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. Let us now see what an ellipse means. We are going to perform an activity using a blank paper, 2 pins, a board on which a paper can be fitted, and a pencil or a pen with a string. Here, the pins are going to act as 2 foci, and using these we are going to draw an ellipse. An ellipse has 2 foci, and at one of the foci the Sun is there in our solar system. The ellipse suggests the orbit of a planet going around the Sun. What happens when we move the 2 foci closer? Let us check. You can see that the ellipse is getting closer to the shape of a circle. And when will it be a circle? Let us see. When the 2 foci are not different but the same point, then we get a circular orbit. All the planets in our solar system go around the sun or revolve around the sun in an orbit that is slightly elliptical or almost circular. As compared to the other planets' orbit of Mercury is a bit more elliptical in shape. If we look at the orbits of comets, for example, Halley's comet, we can see that these orbits are highly elliptical. There can be three types of orbits: elliptical, parabolic, and hyperbolic of celestial objects. The comets having highly elliptical orbit are periodic comets. That is, they visit us in a particular period of time, like Halley's comet visiting us every 76 years. There are some comets which are called as long period comets, like the comet Neowise, which was seen in this July. The longer period of the comet is due to its parabolic orbit. There are some comets or some objects, those may visit our sun only once and never to return. Such objects generally have hyperbolic orbits. A few years ago, an interstellar object named Oumuamua visited our solar system. Yes, it was the first object which was from outside our solar system. So it was a guest object to us. So this was about orbits. Now let us see what the second law of Kepler means. Here we have drawn an ellipse, and on one point a person is going to stand. The person represents the planet. A line segment is joined from the position of the person to one of the foci of the ellipse, where the sun is supposed to be there. The law of equal areas suggests that as this person is going to jump from one tile or one sector to another sector, as the planet is getting closer to the sun or closer to the foci, the speed of the planet is going to increase. And as it goes away from the focus, its speed is going to decrease. Let us see what we can see over here. Observe how the person has to jump fast as it is coming closer to the sun or closer to the focus, and how he has to jump slower as it is going away from the focus. It is fun to try this activity on yourself. In 1768, Johann Bode published a formula. It was a formula based on a pattern he had found out from the average distance of the known planets. At that time, we only knew 5 naked eye planets: Mercury, Venus, Mars, Jupiter, and Saturn. In this formula, there was a gap in between Mars and Jupiter. Bode predicted the existence of a planet after Saturn. In 1781, William Herschel had discovered Uranus at the distance that was near to the distance predicted by this tedious Bode law. In 1801, Piazzi had discovered a planet named Ceres in the gap that was kept in the tedious Bode law between Mars and Jupiter. Observations of planet Uranus had shown that the orbit of Uranus is getting perturbed or disturbed by something. So, it was predicting the presence of something else that is affecting the orbit of Uranus. In 1846, John Adams Couch and Leverrier independently led to the discovery of a planet Neptune that was affecting the orbit of Uranus. However, the presence of Neptune was not the only thing that was affecting Uranus' orbit. There was something else. Scientists named this mission as Planet X. In 1930, Clyde Tombaugh discovered Pluto that was affecting the motions of Uranus and Neptune. Titius Bode law was of course discarded. So it's a discarded hypothesis, as it wasn't based upon any mathematical ground. Also, it didn't predict the presence of Neptune. However, there is a fun activity which we all can do ourselves to understand the solar system distances using this Titius Bode law. Let us now see how to learn about the solar system distances using Titius Bode law. The law tells us that as we go away from the sun, the planets are placed at a distance that is almost twice the distance of the planet before it. It means that if Mercury is placed at an average distance x from the sun, Venus will be placed at the distance 2x from the sun. Let us do a fun activity. All you need is an A4 paper and a pen or pencil. In this model, we are going to consider the objects starting from Sun to the Pluto. So, at one edge along the length of the paper, there is Sun, and on the opposite edge, we have Pluto. Now, what we have to do is to write the distance, the average distance of Pluto at the edge. That is approximately 40 astronomical units. The Sun is at 0 astronomical units. Now, if we fold the paper in half along the length, we reach across 20 astronomical units, around which Herschel had found Uranus. The distance of Uranus we know is about 19.2 astronomical units from the Sun. Now, we have to fold the paper further from Uranus to Sun in half. Here, around 10 astronomical units, we mark the position of Saturn. If we fold the paper further in half between Sun and Saturn, we get the position of Jupiter, which is around 5 astronomical units. If we fold from Sun to Jupiter in half, there was the gap kept by Bode, as there was no planet known at that distance. But later, Ceres was discovered by Piazzi in 1801. That represents our asteroid belt. Now if you fold the paper in half from Sun to asteroid belt, we will get the distance to the Mars. You can see how closer we are going to the Sun now. It is going to be a bit skillful to fold a paper now. If we fold from Sun to Mars, we'll mark Venus there. And where is Earth? The Earth is at 1 astronomical unit. The Mars is about 1.75 astronomical units. And the Venus is at about 0.7 astronomical units. So the Earth lies in between Venus, closer to the Venus, and further away from the Mars. If you can fold the paper between Venus and Sun, the smallest of the possible distance and the smallest of the fold which needs skill, you can mark it with Mercury, the closest planet to the Sun. This is a simple activity which every one of us can do, and we can see how our solar system bodies are placed in the space from the Sun. If you observe the inner planets Mercury, Venus, Earth, and Mars are much closer to each other. And the outer planets, Jupiter, Saturn, Uranus, and Neptune, are more distant from each other. The distance to the planets from the Sun, suggested by TTS Bode law, and the actual distances of these planets are shown here in this chart. We all now know that Ceres is one of the asteroids in the asteroid belt that lies between Mars and Jupiter. Also, Pluto is no more a planet. It is termed as a dwarf planet. Along with curiosity, technology keeps getting advanced. This resulted in landing humans on the moon. In 1969, for the first time in human history, Neil Armstrong and Edwin Aldrin succeeded in touching the surface of the moon. And in 2020, here we are, planning to reach the moon again. Are you interested in spotting the landing site of Apollo 11 yourself on the disk of the moon? All you have to do is observe the moon. Here is a map of near side of the moon. Near side is the side of the moon that faces the earth every time. You can see a name called Sea of Tranquility or Mare Tranquillitatis. In this mare, Apollo 11 landed in 1969 in this Mare Tranquillitatis or Sea of Tranquility, where human touched the lunar surface for the first time in the history. Along with exploring the universe beyond our solar system, we should also remember that there are many mysteries lying around, getting to be known in our own solar system, in the closest neighborhood of us.
I hope you all have enjoyed the video. And of course, when we have talked about so much about the solar system bodies, from asteroids, comets, planets, and moons, we haven't forgotten about our only star, the sun. As we started with the sun, solar eclipse. So, there are some activities which I want to share about solar eclipse. Solar eclipses are astronomical phenomena which occur because the moon covers the disk of the sun. So here is a simple activity which you can try out to understand how solar eclipses occur. I have two disks here. Here is one CD and here is a smaller disk. You can see how much smaller this disk is. Okay. So you must have observed that as you come closer to any object, the object appears bigger in size. And as we move further away from any object, the object appears smaller. However, the size or the actual size of the object is not changing at all. So what is happening here? How can a moon that is much, much smaller than the sun, to be exact, it is 400 times smaller than the sun, can cover the whole sun? As we saw on 21st June, it covered 98% of the solar disk. So how does that happen? It is because the moon is 400 times closer to us, closer to the earth, and thus it can cover the solar disk. So what is actually happening? When we talk about solar system bodies or the sizes, we are actually talking about angular size of the celestial object. Now what is meant by an angular size? Let us see. So here you can see, this is when we measure a diameter of this disk, This is going to be the actual size of this object. But as I am keeping this object in front of me, the angle this object is making with my eye, okay, with the observer's eyes, is called as the angular size. Now, if you observe, as I take this object away from me, you can see that the angle goes on decreasing. As the object goes farther away, the angle is decreasing, and thus the angular size of the object is getting diminished. So, as we learned, the sun is 400 times bigger than the moon, but it is also 400 times farther away from us than the moon. So what happens is, if you can observe this, as the moon is closer, it can actually cover the whole disk of the sun. This can be, this is actually telling us how the total solar eclipse occurs. And when does a annular solar eclipse occurs? You might have heard that the orbit of the moon around Earth is not circular. It is elliptical. So what happens is, moon sometimes is much closer to us and sometimes it goes away from us when the angular size of the moon gets smaller. And here you can observe that you can see the outer ring of this disk. So this is the case where annular solar eclipse is seen. So these are some fun activities which you can try yourself. And apart from that, I also want to share that we haven't learned 100% about our own star yet. And to learn more about our star, on which our lives are dependent, which is the main energy source for us, we humans have been sending different spacecraft in the space to learn about the sun. India is also going to send a mission known as Aditya L1 very soon in the space to study our own star, the sun. With that remark, I would like to hand over the session to my friend Ankit here. So we'll go for the live question and answer sessions with IUCAA research scholars. Ankit, please take over the session.
Thank you, Sonal. Hello, everyone. A very warm welcome to you and a very good afternoon to this Pulastya 2020 question answer session. Today we have with us research scholars from IUCAA. Let me introduce them to you. So we have with us Vaishak Prasad, and his area of research is gravitational waves and numerical relativity. Then we have Yash Bhargava, whose area of research is black holes and its accretion disk. Then we have with us Siddharth Maharana, whose area of research is interstellar dust, telescopes and instrumentation. And we have with us Ruchika Seth, whose area of research is extragalactic astronomy. So they will be answering to all your questions which you have sent to us via Google Forms, and also we will be answering to all your questions live. So I kindly request you to please type in the questions to us in the chat box, and we'll be taking up your questions. Now, this year, the Nobel Prize was given for physics was awarded to 3 people. That is, the one half prize was awarded to Roger Penrose, Professor Roger Penrose, for the discovery that black hole formation is a robust prediction of the general theory of relativity. And the other half jointly was awarded to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. So we have received a lot of questions related to black holes. So we will just start off with the questions regarding black holes. So I would request Yash. My first question is to Yash, that what are black holes and what is inside a black hole, and what happens if a light or matter enters it? Over to you, Yash.
Uh, Hi, Ankit. Thanks for the question. And it seems a wonderful compilation of the questions about black holes. So, firstly, what are black holes? So, black holes are basically a hole in the space-time. So, what does that mean? So, what happens is if you have a large amount of mass, which is basically concentrated into a very small point, it creates a what you'll say a hole in the fabric of space-time. So if any matter which ventures past through it, it will get sucked into the black hole if it has the correct angular momentum, as I would like to call it. And okay, so that is basically what a black hole is. What is inside a black hole? Well, it's a very interesting question because we can't answer it. So black hole, as we know, sucks everything in, including light. And since it has such a large amount of gravity that even light cannot escape, so any information which basically travels at the speed of light cannot escape. So we cannot get any information out of a black hole and what is inside. Well, some people have speculated, and I'm pretty sure most of our audience would have seen in the movie Interstellar, which was had a very realistic description of how the outside of a black hole would look like. But they speculated what could be inside a black hole by their like in their theories. And how do you find out? Well, it's a very interesting question, and I would encourage our young viewers to probably take up research on it and try to answer this question.
That's
And
great.
yes, and so what is significance of basically researching black holes? So when if you try to develop something like a theory of what a black hole might be or how to answer it, it actually leads to a very interesting uh, uh, epochs of understanding. So firstly, we can basically understand our universe a bit better. We can understand what happens at a very large or very small scale in the universe, and what and it also leads us to leads to basically making of a very precise instrument which can have major implications in understanding of and it has further uses in probably in real life as well. That's it from me.
Okay, thank you for the answer. That's a really good answer. Second question from Jayesh is that do wormholes exist in the universe, and how can we make a wormhole? It is a very weird question. Jayesh is a 15-year-old kid, so he has asked this question out of curiosity. Vaishak, could you please take up this question? Over to you, Vaishak.
Yeah. Thanks for reading out the question. I hope you can hear. Please confirm. Hello.
Yes, you are audible.
Can you hear me?
Yes. Yes.
Okay, great. Okay. So, okay, let me try to answer this. Do wormholes exist in the universe? That's a wonderful question. Wormholes, as you know, are bridges which connect very distant regions of space-time. Space-time as described by Einstein. And these allow for quick travel to distant parts of the space-time, faster than what one would usually have to take. So do wormholes exist in the universe? Well, wormholes are definitely a theoretical possibility from Einstein theory and the other theories of gravity. And we know that most of the observations that we have conform with the predictions from Einstein's theory. So it's theoretically, of course, existing. But however, do they exist in the universe? That is an important question. I'm afraid it's probably a little bit too early to answer that. We do not know. There is no observational proof of the existence of wormholes yet. And we also know that wormholes require a special kind of matter to keep the throat open so that you can go through it. So whether or not such special kind of matter can exist or not, I mean, we are not sure about that. And how can we make a wormhole? Well, these are outstanding research questions, and I would say actually, if you want to work on these questions, of course you can. These are very difficult topics. These are related to what is known as topology changes in the space-time. We do not yet know how you can make a wormhole. We only know that it would require very large amounts of energy to create them. Yeah, that's my answer.
Yeah, that's great. So we have a live question from a viewer, Dalika Joshi, and her question is related to black holes, to which Yash had responded. Dalika asked that what does it exactly mean when we say information is lost inside a black hole, and what is the black hole information paradox? Yash, could you please answer the question?
Yeah, so what do we mean when we say that the information is lost inside a black hole? Well, so the idea is that basically these are some thought experiments which people have done. So since we have not approached a black hole with ourselves, we can imagine what will happen if we approach a black hole. So suppose if you have two observers, one standing far away from the black hole and one trying to go towards the black hole. So the idea is that one person will see that other person is falling in and he's basically getting stretched and what we call as spaghettification. So basically he'll turn into very thin strands of matter. But the other person will, we expect to see that that person is, the time for that person has stopped basically. So he'll see that the other person is just growing old and stuff like that. But so there is a discrepancy in what each of them are seeing, but it's not technically a paradox because there is no discrepancy as such, because it's all based on the frame of reference of who is the observer in particular. And the thing is that we don't know what happens to the information which goes into the black hole, so we can't comment like what is happening to the information which is going inside a black hole. Like, if does it retain the entropy which the black hole like which it originally had? Like, that is the question which we need to answer. And yeah, that's it.
Thanks. Yeah. So we have one more.
Ankit,
Yeah.
can I add a few lines to
Sure,
answer?
Yeah.
Okay,
Yes,
thanks.
please.
So the question was on black hole information paradox, right?
Yes.
Okay. So what I would like to add is that the black hole information paradox is actually a paradox which emerges mostly because of the combination of quantum mechanics and black holes. Black holes, as described by gravity, which is presently a classical theory, what it says is that black holes can be described by just at most three parameters, mostly major parameters, which is mass, angular momentum, and charge. And however, in quantum theory, we have particles with various different characteristics. We have things called quantum numbers, which can be used to distinguish between different types of particles, and they have other details in them. So whatever object you throw into a black hole will definitely disappear inside it, that we know. But however, the black hole is only described by three parameters: mass, angular momentum, and charge. So what happens to the other details of the particle which has fallen inside the black hole? So this is the paradox which is existing. And recently there have been some resolutions that have been proposed, which are being investigated more closely now. Thank you.
Thanks. The next question is from Jitesh. So he is asking, how do we observe gravitational waves? And since they are very weak, how do they penetrate Earth's atmospheric layer? So, Vaishak, could you please answer this question as well?
Yeah, sure. Okay, so that is a wonderful question. So indeed, gravitational waves are very weak. In fact, they are the weakest of the forces that we know. And they are also long-range forces. And because gravitational force do not interact strongly with the other kinds of forces which exist in nature, they are also not disturbed by the presence of matter, for example, in space-time. So we know that if you shine a laser through a glass slab, the path of the laser changes because it interacts with the atoms, the electric and magnetic field of the atoms in the glass. However, if you shine a gravitational wave through a slab of glass, if you could do that in a lab, then the gravitational wave passes through the slab almost undeterred. It does not suffer any change just because of the fact that it weakly interacts with matter. So this is the reason why gravitational wave allows us to see into parts of the universe which cannot be probably observed or probed by using electromagnetic waves and the other forces, including the primordial gravitational waves from the Big Bang, if it exists. I hope that answers the question.
Yes, and again, the next question is asked by Shraddha. So she is asking that as the world is investigating a lot for finding gravitational waves, black holes, and other cosmic events and objects. But as a common person living on Earth, how and when we will get the benefits of these discoveries? So. Vaishak, can you please answer this question? The other panels members also can join in. Vaishak, you are on mute. Please unmute.
Ankit, I lost a part of the question to
Yes,
discussion. Can you
yes. So Shraddha is asking that as the world is investigating a lot for finding gravitational waves, black holes, and other cosmic events and objects, as a common person, when we will get benefit of these discoveries?
Yeah, does someone else want to take up the question, or should I take this up?
Ashak, you go ahead. I can join in if you miss something.
Okay. So, well, these are very nice questions indeed, but they cannot be completely answered now because it is only recently that we have started detecting gravitational waves. I can imagine the situation was probably similar when the electromagnetic waves were discovered back in the 19th century. So what I would say is that we are learning a lot about the objects, the celestial objects in the universe, and the gravitational waves provide us a way to understand details of those objects, the universe, as you pointed. However, are they going to enter into our everyday lives for practical use? I'm afraid if it even does, it won't be in near future because of the fact described in the previous question that gravitational waves are very weak, and we are presently trying very hard to detect them. It's a technological marvel, actually, the LIGO detectors that are able to detect such weak gravitational waves. We are just gripping with that. So let's wait and see what happens. That question cannot be answered right away.
Yeah, thank you. So the next question is asked by this is asked by Amit Kumar and Adesh Pingle. So they ask that when and how the life cycle of the star starts, and how stars are born, and when the life cycle ends. So Ruchika and Yash, could you please take this question up?
Yeah, sure. I'll take this one. And yeah, so basically, stars are very peculiar objects in some sense. So what happens is a life cycle of the star is typically you can determine on what the initial mass of the star is. So let's say you have a very giant cloud, not the clouds which you see on Earth, of course, a very huge giant cloud. And typically, since our universe is mostly composed of hydrogen, this will also have a large amount of hydrogen in it. So what happens is when you have this large cloud, it will slowly come together, and over years and years and years, it will finally collapse into one small being, which is known as the star. And if it has a certain mass, then it will glow, and maybe you can like it then it has a huge life cycle. Like, so our sun is basically excuse me. Yeah, our sun has a life cycle of almost 10 billion years, and it has only used up half of its life. So you can imagine how, like, if so these stars are very long lived, and if a star is much more massive, it consumes this matter at such a high rate that it will collapse even faster. So what happens is, if you have a star which has mass of typically around the sun, what will happen is it will basically become a red giant, and it will become so huge that it will actually cover the orbit of Venus and probably squats the whole Earth as we know it. But don't worry, it will take around 5 billion years from now. So and then once it does that, slowly it will lose the core. Like at this point, helium is burning inside the sun, and once helium runs out, what will happen is it will just disperse the extra amount of gas it had, and what will be left is a core of white dwarf star at the center. So that's one way to go. But there's another way which is much more interesting. It is also known as supernova. So what happens is, if your star is say 10 times massive than the sun, then what will happen is helium can burn, and it will allow the core will go so hot that you can burn even higher elements. And once it reaches iron, it cannot burn any further, and what the whole star collapses and it implodes, and you see a giant explosion which can be seen even galaxies away. So at after it explodes, if the star has a particular mass, then it will become a neutron star. But if it is much more massive than that, then it will become a black hole. And that's how you basically get stellar mass black holes in our universe. uh, Yes, I think I have answered all the parts.
Yes, yes, yes. And Ruchika, would you be adding some points to this? Ruchika, am I audible to you?
Ruchika, you are on mute.
Okay. Hi.
Hi.
Yeah. So no, this is fine. This is a good answer. Uh, I don't
Okay.
have.
Okay.
Yeah.
So the next question is asked by Kirtana Rajan. She is asking that how do black holes produce their enormous jets of hot, fast matter?
Hmm. I think it's a
So
very.
yeah,
I'll take up this question. Okay,
yeah,
so
yeah.
this
Please
is a
go ahead. Yeah.
very good question. It's still an open problem in astrophysics how the how the black holes are producing jets. But as far as our understanding goes, so there's an accretion disk in the plane of the black hole, and when the black hole is rotating, it is accreting matter, which is basically stars and dust and gas clouds and everything. So as the black hole rotates, it accretes the matter. The matter loses its energy, and this gravitational potential energy basically lost is given in the form of radiation. And at some point, there is a magnetic field. I mean, again, it's an open problem, but we presume that there's a magnetic field along the axis of the black hole on which it is rotating. And so this magnetic field traps the accreted matter, and there's a synchrotron force with which the matter basically follows the magnetic field lines, and that's how the jets are produced. And they are given off the plane of the accretion disk. So if this is the accretion disk, this is how the black hole is rotating. The matter or whatever the black hole could accrete is given in this direction, which is perpendicular to that plane. And this matter is again, it's an open question, what are these jets made up of? But it's made up of electrons and positrons and atoms. That's what we think. And this emits in synchrotron radiation, uh, due to the magnetic field and the charged particles.
Thank you. So again, we have a very interesting question. So how to find and study exoplanets, and what are the problems one faces while trying to study the exoplanets as compared to the observation of stars? So Siddharth, would you please answer this question?
Yeah, I can try and answer this question. So, actually, this field of finding exoplanets and understanding them is currently one of the most actively pursued areas in astronomy right now, and a lot of big projects are coming up to carry out this to find answers to this question. So, I'll first tell what is the challenge and how we are trying to find a solution to it. So, the challenge in finding exoplanets is that the exoplanets are small in comparison to their stars. So think of something like a Earth rotating around the sun, and the problem is that these are very small objects, and these are very faint compared to a star. So the host star will be millions or billions times brighter than the small planet which is rotating around it. So it's very difficult to locate that star, locate that planet around that star. It's the same reason why we cannot see stars during the daytime, because the sun's brightness is so bright that it makes everything else on the sky invisible. So that's the problem. So there are two problems basically. It's the planet is very small and very near to the star, and the star is so much brighter. So that is the challenge in how why it's difficult to find exoplanets. But then because it's a scientific problem, and scientists try to figure a solution which can overcome these challenges. So right now, with the current generation of biggest telescopes, which are 10-meter class telescopes in optical wavelengths, people are trying to uh, do something called coronagraphy, which is they block the light from the star so that all starlight is blocked, and then we can try and find the small planet around that star. That's one way of doing it, which is called direct imaging of exoplanets. There's another way in which we look at the what is called the spectrum of the star. The spectrum of the stars basically contains all the emission lines and the absorption lines. That's okay. But if there is a planet around the star, it creates some wobble in the star's motion. So because of this gravitational effect, and that wobble leads to some change in the spectra, in the sense that the spectrum lines go to either bluer side or the redder side. So by looking at that spectra and see how the spectra changes over time because of the wobble created by the planet, we can find we can estimate what is, if there is a planet around, and what is its mass and distance and some other characteristics. So those are two basic ways of major ways of finding exoplanets as of now. Either to directly detect the exoplanet by using state-of-the-art technologies to block the starlight, and the other way is to seeing the spectra and what is called transit, not transit, sorry, it's called radial velocity measurements. I missed the third one. Third one is called the transit, where you see how so imagine there is a star and a planet comes in front of it. The planet will block some amount of light from the star. That will lead to some minor reduction in the brightness of the star. So tracking how the brightness of the star changes, we can see if there is a planet orbiting around it. So it's an indirect way of detection. So basically three ways of detection of exoplanets. But it's a field that is really kind of picking up. So we'll find more and more exoplanets in the years coming by.
Yes. And again, there is one interesting question asked by one of the students named Sarthak Gadge. He is asking, is there a planet like Earth and star like a sun in other part of universe? And connecting question asked by Arya Shri Shrimal is that, what if we find aliens? So Siddharth and anyone on the panel, could you please answer this question?
I'll start off with the first question, and
Right.
then
Yeah.
others can join if
Yes.
if they have anything else to add. Regarding whether there are stars like Earth in the universe, there are like billions and billions of stars like
Right.
Sun in the universe. I mean, we are in no way around any peculiar or a different type of star. It's a very common star in a very common galaxy in the universe. So there's nothing special about our solar system in some sense. Are there planets like Earth around stars like Sun. There are planets like Earth in terms of mass and size as well. But again, it's a field that is really in its very nascent stage. In the coming years, we'll find more and more planets like Earth. So my guess is that we will find again probably millions of planets like Earth. We already have some planets like Earth around stars. We'll find more of them in the coming decade, probably, where the technologies to find them becomes more mature. Regarding the question about the aliens, the question was like, what will we do, or what is it? What was the question?
So the question is, what if we find aliens?
That's a Nobel Prize. If we find aliens, but we don't know. We'll see. First, we're trying really hard to find life elsewhere in the universe right now. A lot of astronomy's efforts right now is to find life elsewhere using these exoplanets. So it's a question we are trying very hard to answer, and it will be great if we can find.
Yeah. So moving forward, so the next question is asked by Asfaq Badarka. So he is asking, what is exactly a photon, and why does a photon move like a wave and not in a straight line or other path? So Vaishak, could you please answer this question?
Yeah, sure. I try to answer this one, and others can add on if there's something I'll leave out. So this is also a nice question. What is a photon? Well, it's not very easy to answer, but early in the 1900s, it was found that the electromagnetic waves, the energy in the electromagnetic waves are quantized. So this, for example, started with the black body radiation, the treatment of the black body radiation, and then the treatment of photoelectric effect by Einstein. So it appeared as though the electromagnetic waves do not, the energy contained in the electromagnetic waves are not continuous, but they are quantized. So each of these pieces, quanta, can be called as a photon. You can answer this question as various levels. If you look at it from the point of view of quantum field theory, then you would basically say that a photon is basically depends on the energy state in which the field is. So the excitation level of the quantum field gives you the number of photons that is represented by it. And why does a photon move like a wave and not in a straight line or other path? Let me rephrase this question. I would ask why does a photon behave sometimes like a particle and sometimes like a wave? So this thing is not particular to just photons. They are generic for particles of smaller sizes, actually for all particles, but we can observationally, experimentally see it for particles of smaller sizes, that they sometimes show wave-like properties and they sometimes show particle-like properties, and sometimes both. So this happens because objects in the small scale world, like very small sized objects, they don't behave like what our intuition suggests about the everyday objects that we come across, like a ball or a bat or a water bottle or whatever we see. So, or water waves, for example. Water waves are one example of waves that we are familiar with every day. It is so observed that for particles of smaller size, sometimes their behavior can be explained with their wave-like nature and sometimes with particle-like nature. So this is described by quantum mechanics. The wave-like characteristics, for example, are diffraction and interference, which we see in light, which is how you can conclude that light is a wave. But on the other hand, if you look at the Einstein's treatment of photoelectric effect, there you could interpret light photons as particles. So this is the dilemma which is existing for small objects. The next part of the question is, let me read that. How atoms absorb photon energy and go to an excited state. this is also a very interesting question, and we understand this. So basically, you know that different forms of energy can be interconverted. Basically, if you place an atom in an electric or a magnetic field, then the atom, the electron, so we know that the atom is made up of protons and electrons, and they of course have charges on them, and therefore the electromagnetic field of the constituent of atoms interact with the external field, and there can be an energy exchange from the field to the atoms. And if the atom can absorb exactly the amount of energy required for it to go to the next state, which is discrete by virtue of quantum mechanics, then it goes to an excited state. Yeah, I hope this answers the question.
Yes, thank you. Okay, so the next question is what is multi-messenger astronomy? Siddharth, can you please answer this question?
Yeah, I can try and answer this question. So the idea behind multi-messenger astronomy is that the signals from this come to us across the electromagnetic spectrum. Sometimes they are in X-rays, sometimes they are in UV, sometimes in optical wavelengths, and then in radio. And apart from electromagnetic wavelengths, there's also information in terms of gravitational waves or neutrinos or high energy particles. So these are different ways in which information from an astronomical source can arrive to us. Now, if to understand some objects, it becomes very essential to use all of these methods to understand what is happening in the system. For example, a good example is the neutron star merger event that we detected, I think last year or a year before that. So we astronomers had been predicting that two neutron stars should merge together, and that should give us gravitational waves, and then after some time there should be an X-ray flare, and then there are theories about what would happen after that. So a neutron star merger was detected by LIGO detectors, and after that we found X-ray signal, and then in optical, and then now it's being studied in radio wavelengths as well. So from that we got multiple sources of information about that system, and it helped us understand the system better. So that's basically the idea of multi-messenger astronomy. So where you use multiple sources of information encoded in the different wavelengths and get a more complete picture of the astronomical object than what is available with just one type of wavelength or one type of messenger. That's a basic idea.
Yeah, thanks. There is one more question, live question from Devashish Mishra. He is asking, what are the different theories of our moon's formation?
I don't know much about that. Maybe somebody else knows, is more informed on the subject than me.
Anyone from the panel? Yeah, Ruchika, go ahead. Yeah.
Okay. What the popular belief or the scientific belief goes is that moon was once part of the earth, and it's something which collided with the earth billions of years before, and now and then it detached from the earth, and now it's orbiting, and the observation suggests that the moon is going far away from the earth as the time goes, so the orbit of the moon is ever increasing. And so that means if we extrapolate that back in the time, there was a time when the moon was very close to the earth, and hence it's thought to be a part of earth, and at some point of time. So that's one theory I am aware of.
Right. A very good question and important question. Which are the current and upcoming observing facilities and projects in India? So this question is for the panel. Also, Siddharth, could you please answer this question?
Yeah, I'll answer the question, and if I miss something, others can pitch in.
Yes.
in terms of astronomical facilities, there are lots of facilities right now. In the optical, we have 2-meter class telescopes. One is called the Himalayan Chandra telescope at Halle in Ladakh. One is near Pune. It's called Giravali Observatory, IUCAA Giravali Observatory, run by IUCAA. And the third big one is it's called Devastal Optical Telescopes near Nainital. That's around a 3.4-meter class telescopes. So these are the three biggest telescopes in the optical wavelengths. In radio wavelengths, we have the large telescope array called GMRT, Giant Meter Wave Radio Telescope, near Pune, which is one of the biggest facilities around the world. That's one. And then we have for the short wavelength, which are the high energy wavelengths, which is ultraviolet to X-rays. We have the AstroSat facility, which is a satellite telescope that has been in the sky since 2015. So right now, these are the major facilities that I am aware of. Uh, in future, there are bigger telescopes and facilities coming up. In the optical domain, India is involved in what is called the 30-meter telescope. So the mirror will be 30-meter class telescope, 30-meter mirror. And because these projects are so big and expensive, these projects cannot be made by one country. So India has joined a collaboration of other countries like US, China, Canada, and to build this 30-meter class telescope. This telescope will be located in Mauna Kea at 4,000-meter altitude in Hawaii. So that's the upcoming big facility in optical domain. In radio, India has tied up in a similar international consortium with other countries to uh, build the square kilometer arrays. So this is a set of radio telescopes that will be installed in South Africa and in Australia. And the idea is to use something called aperture synthesis to make an equivalent radio telescope of the size of like thousands of kilometers. So that is another big project. Then there's LIGO, in which India is involved in, where we are making the third um, LIGO detector in Maharashtra. Uh, these are the upcoming big projects that I can think of right now.
Uh, there is one space mission which is being launched probably in 1 or 2 years. Daksha, which is a detector system for gravitational wave events. So that is another one.
Yes.
Yeah, and I missed one which is called Aditya L1 mission, which is
Yes,
a
yes.
a sun-dedicated observatory that is coming up. It will be similar to AstroSat in the sense that it's a space-based mission. It will have multiple instruments, UV and maybe some optical. I'm not sure about that. It has a UV telescope, and then there's other probes to find us to study the sun. It will be located in a position called L1, and this is being built by multiple institutes in India to be launched in probably the upcoming year. Yeah.
Right. So, so one more interesting question. This is about women in STEM. So, what should be the approach of young women towards research in the current scenario? So, Ruchika, would you like to answer this question?
Okay. I think we as women should have self confidence. We should not undermine our abilities. And well, yes, it's tough at times because you will know that you are in minority. But I would say gel in with the guys. They are very helpful, and don't hesitate to ask questions. Sometimes we overthink and we don't ask questions, or we think it's stupid. I think the best way is to be vulnerable, to put up questions, to admit that if you don't know things, and go with the flow. So there is nothing to worry about. People are very open, and yeah, seek advice from your classmates and seniors, and yeah.
Right. One more interesting question which is asked is that what are the career opportunities in astronomy, astrophysics, and how engineers can contribute in astronomy, astrophysics field? So I kindly request Siddharth and the panel to answer this question.
Yeah, I think it's a question that we often get asked very commonly,
Yes.
very frequently. Especially people like me and Yash who have come from engineering background into astronomy. For engineers, I mean, there are a lot of opportunities. Astronomy in general is a technology-driven field. To give you an idea of what that means is that new discoveries in astronomy have often happened when we have built a new kind of a detector or new kind of a telescope. So astronomy, then in that sense, is a very technology-driven field. So engineers have a big part to play in developing the new kinds of detectors or telescopes or and systems to probe the universe in new ways. So in that sense, there are a lot of opportunities, and because there are so many opportunities, it's very difficult to pinpoint to say what is the one way to do it. There are multiple ways in which you can contribute. If you're a mechanical engineer, you can help build systems, mechanical system for the instruments. If you're an electronic engineer, you can build the electronics. So every instrument has different kinds of, it's a combination of different types of engineering, and based on your interests as well as your training, you can contribute in your own way. So that's the engineering side. I mean, if you want to get involved in engineering side, in the same way, in another way, what has also has happened also happens is that a lot of people from engineering background come to astronomy and don't necessarily do engineering in astronomy, but pursue scientific questions. So depending on your interests, you can choose to do either. There's no restriction uh, that will limit you to what you want to do. Yeah, maybe Yash can add more because he has also come from engineering background.
Right.
Well, it's not that difficult and it's very interesting. So, like, why not?
Okay, and connecting question to this is which is asked by Arun Kumar, a class 12 student. He is asking that uh, he wants to study about the universe. So what should he do after class 12 so as to get into astronomy and study the universe?
Well, you can join either a science field where you actually study the basic physics required to understand the universe, or you can probably specialize in engineering physics, which will help you design equipment which you can later use to study the universe. So there are two ways which I can think of, but there are many different approaches, and you should do what you like the most.
Okay. Uh,
Just to
so
add, I mean,
yeah.
I think to summarize both mine and Yash's answer, there is no one way of doing it. You can choose either way, and you can still contribute to astronomy uh, in whichever way you want. So there's no
And if you
strict.
just want to learn, then Wikipedia
Yeah.
has an interesting amount of resources, and probably the Science Center people from IUCAA also have a repository of resources which you can get to by contacting them.
Yeah.
Yes. So, there is one more interesting question, live question asked by Vinita Kulkarni. She is asking how many black holes are there in the whole universe. So, Yash or Vaishak, can you please answer this question?
Well, there is one for each galaxy, and
Yeah,
probably more,
correct.
I think, because our galaxy has lots of black holes. So yeah, very much, quite a lot, quite a lot.
Right. And another question which is asked by Vinay Sonone. This is for Vaishak. He is asking what are black holes incomplete wormholes?
Okay, wow. I mean, that's a very cool question, actually. So I won't answer it completely because I can't, firstly, but I will tell you what we know already. So there is an interesting connection between black holes and wormholes. And I would advise you to look into what are known as Einstein-Rosen bridges. So back in the 1900s, after Einstein found out his general theory of relativity, and black holes solutions were also found, and quantum physics was also found, then Einstein started speculating that whether black holes can be black holes with a throat, the interior of black holes with a throat, with the Einstein-Rosen bridge, can be used to explain particles in nature, particles like electron or various particles that we know of. So the short answer is that the interior of black holes can contain throats, which connect to probably other parts of the universe. But the throats which I know of, the Einstein-Rosen bridges, they close in very quickly before you can pass through them. So unless you can travel faster than the speed of light, you cannot make it through the tunnel. Honestly speaking, nobody knows what is in the interior of black holes, because we do not receive any communication from the interior. All we know about is the exterior, and that we know for sure from Einstein's theory, at least. So yes, the answer is speculative at best, and Einstein-Rosen bridge is what we should look for. Thank you.
Yes, thank you. The next question is asked by Sujan Dhali. Do black holes merge into themselves? So, Vaishak, can you answer this question, please?
So if I understand right, are you asking what is the end product of merger of two black holes?
Yes.
Correctly?
Yeah.
Okay. So I would say yes. Two black holes, when they merge, we expect the end product to be another black hole. If two stars merge, the end product can be another star or a black hole, depending on its mass. Yes, when two black holes merge, we expect it to form another black hole. That's correct.
Right. So there is one more question. What are the types of galaxies, and what is Saraswati supercluster? Ruchika, could you please answer this question? You are on mute.
Yeah. So can you repeat the question?
Yeah. So what are the types of galaxies, and what is Saraswati supercluster?
Okay. So galaxies, if you're asking the morphology of the galaxies, there are two types of two major morphology types. One is the spiral galaxy, which is our Milky Way, our nearest neighbor, the Andromeda, and another M33 galaxy in our local group. So these are spiral galaxies. These are young galaxies, and they are star forming. They are presently full of gas, and a lot of stars are being formed there. Although our Milky Way just forms one star per year. Then there are elliptical galaxies. Okay, elliptical galaxies are like the ellipsoidal galaxies, and they are the second majority class. And the elliptical galaxies are old age galaxies. So they are not currently forming stars. They don't have star gas to form stars, and they actually are formed by the merger of spiral galaxies. So when two spirals or many spirals merged, they became an elliptical. The another class of galaxy is a dwarf galaxy or an irregular galaxy, which do not have a shape, and you can say they are sort of proto galaxies, which are forming in the universe at the present epoch. So they are not fully formed galaxies, but they are just some dark gas clouds yet to form stars. So irregular galaxies, you can say they've started forming stars, and now they have evolved to become a galaxies. And there are proto galaxies which are not yet galaxies. And yeah, so these are major four morphological classes of the galaxies, you can say. um, yeah, I think I've answered your question.
Uh, yeah, okay. So the next question is asked by Sujan Dali. He is asking that why there is so much gravitational pull in black holes, and what actually happens to the light or matter when it enters the black hole. So, Vaishak or Yash, could you please answer this question?
May I take this question? And Yash can add to it maybe.
Go ahead,
Please.
go ahead.
Okay, thanks. So the first part of the question is, why is there a lot of gravitational pull near black holes? Is it right? Have I spelled it out correctly? Hello?
Yeah, your voice. Yeah, so I will repeat the question. Sujan Dhali is asking why there is so much of gravitational pull in the black holes, and what if what happens to the light or matter if it enters the black hole?
Okay. Well, so first of all, black holes are objects, out of all the objects that we know of in nature, black holes are those objects which are the densest that we know of. Actually, according to the classical Einstein's theory, a black hole is just a point, not exactly a point, but it basically contains a singularity at the center, which means all of the mass is compressed into almost a zero volume. That's what the classical theory says. Of course, the quantum theory would not be compatible with this. But let's stick to the classical one. This is just as how my colleague Yash had mentioned. The reason why the gravitational wave is very high, the gravitational pull is very high, is that they are compact objects. They are very dense objects. So the tidal forces will be very strong. Tidal forces are the forces which stretch you if you come close to an object. That's the first part of the question. And as to second part of the question, what happens if light and matter enters a black hole? Let me give you another perspective of what a black hole is, so that it will help us understand what happens in this case. So in other words, a black hole is essentially a region of space-time which is trapped. So trapped in the sense that if you are in the trapped region, and if you're trying to get out of it into an untrapped region, you cannot do it. And light, as you know, is the fastest traveling objects that we know of. And in a trapped region of a black hole, not even light can come out of it. And the horizon is the surface which separates the trapped and the untrapped region in a black hole space-time. So if you shine light or if you throw in matter into a black hole, we can predict what happens to it until it reaches the surface, the horizon of a black hole. But after that, like we had discussed previously, since we don't know what the interior of a black hole is made up of, we don't know what happens to the particle, and we don't know what happens to the information inside the black hole with that particle. And this also connects with the information paradox that was brought up earlier. So the short answer is we don't know what happens to matter when it goes inside a black hole. And if the light is not going inside a black hole, but just moving around in the vicinity of a black hole, then we know what happens to it. It gets bent, and this is called gravitational lensing, which you can look up on. It's very interesting. Yeah, that would be my answer. Thank you.
Okay. So the next question is asked by Dalika Joshi, a live viewer, and she is asking, what are the predictions about the future of the universe? So Ruchika or anyone from the panel can add to this.
Okay. So it depends how much in the future you would like to go. So the what people say, of course, our sun. So okay, I'll start with saying 2-3 billion years. Andromeda is going to collide with Milky Way, and they are going to, as I said, there are two spiral galaxies, and they are going to merge and form an elliptical galaxy. Our sun will not be affected because these are collisionless systems, so the suns won't be affected. But in 5 billion years, our sun will go into not a supernova, but it'll go into a red giant phase, and then it'll become a white dwarf. And our Earth will be finished in 5 billion years for sure. But then in some future, trillions of years, or I don't know what the time scale would be. There is Hawking radiation, and the black holes are going to evaporate, and there'll be no matter, and also cosmologically speaking, we are all, it's an expanding universe till now, and it's an accelerated expansion. So all other galaxies which are not in our local group are going to recede away from us, and we are going to be lost in oblivion, and it'll be just our supercluster which will be together. Some other supercluster will, we won't be able to see that, and yeah, so the space is expanding, and well, the future is dark, but uh, anyway, we are here only for the next 5 billion years. So
Yeah, that's a great answer. So the next question is asked by Apurva Ambike. So he is asking, how does Hawking radiation work, and can we hope to observe it? So Yash or Vaishak, could you please answer this question? Yash.
Vaishak, you want to take this up?
Okay, I'll try. I lost a part for the first part of the question. If you
Yes.
could
So the
repeat,
question is,
please.
how does Hawking radiation work, and can we hope to observe it?
Okay, so okay, I'll try to answer this. Yeah, but it is difficult topic, at least for me. So basically, Hawking radiation is a product of the application of quantum physics to the vicinity of the horizon of black holes. In a very intuitive, in a very rough sense, um, if you take vacuum, basically, which we call empty space-time, the quantum physics says that it is actually not empty. There are continuously particle and antiparticle pairs being created and annihilated. And what happens at the horizon of a black hole is that taking a few words from my previous answer about a black hole being a trapped region in space-time, and the outside of the black hole being untrapped, and these are being separated by a surface called the horizon. So basically, if there is particle and an antiparticle created at the horizon, location of the horizon of a black hole, then one of the particle falls in, let's say the antiparticle falls in, and due to conservation of momentum, the particle falls out. And the horizon being a one-way membrane, you can only enter it from outside, not from inside. Um, the particle which falls in is lost. The antiparticle which falls in is lost, and the particle comes out, and this is what we observe as Hawking radiation. This is what the calculations suggest, and this is a very intuitive picture. Please don't take it literally. This is what Hawking radiation is, and Hawking radiation is pretty weak. So with the present probes that we have, we cannot unfortunately detect Hawking radiation unless we are probably too close to a black hole. And I don't know of any closest black hole to Earth. Yeah, so once we come to know, probably we can go there and test it out, hopefully.
Also, probably if you want to see Hawking radiation, your black hole should be isolated and not affected by another companion star. So if that is the case, then you will probably see accretion disk more, and you won't be able to see Hawking radiation as such. So you'll need isolated black holes, but you can't detect isolated black holes because, well, it's a black hole.
Right. One more question based on black hole is asked by a live viewer, Himanshu Pal. He is asking what will happen if a planet goes inside a black hole. Ruchika, would you like to answer this question?
Okay, so I'm assuming that you are thinking about a binary system where there's a black hole and there's a star, which is, rotating around the black holes. It's like a binary system. And there's a planet of the other star, which is, rotating in the star. So I think when the planet goes inside is when even in the star merge, or the planet okay, it's a bit difficult to visualize the situation, but I think if the planet black hole can of course suck in the planet, there is no doubt about that. And if the planet goes inside the black hole, then it will be lost forever. It's like it just eats up the stuff around it, um, and and then we don't know what will happen to that.
Right.
It's just a merger.
Yes. Yes. Do you want to add to this?
Uh, yeah, sure. So basically, another way to interpret is that as a person who is sitting outside and sees a planet being devoured by a black hole, what will happen? So what happens is it will extend in one direction, but it won't extend in the other direction because of the tidal forces. So this process is basically called spaghettification, which is basically making Maggie out of your whole planet. So it will be basically become long strands, and as the planet moves about, you'll see that it is being stretched out and stretched out and stretched out until that you can see that it's basically stopped in time, and you won't be able to see further extension of it. But for the planet, the people on the planet, they have probably entered the black hole by then. But it is like because of the differences in the time for a person who's sitting outside and the person who is like planet which is being taken in by the black hole, there is a discrepancy and you can't basically tell what is happening.
Great. So the next question is asked by Rutu Shirke. Her question is, does general relativity predict that our universe should have Big Bang or beginning of time? So, Vaishak, would you like to answer this question?
Okay, so these are all Nobel Prize questions that we have been given.
Right.
So, yeah, again, I would start with the same disclaimer that I will answer this question to my limited capacity and understanding. So, there are two parts to this question, if I have parsed it correctly. The first one is, does general relativity predict Big Bang, right?
Yes.
Okay.
Yes,
Yeah.
yes.
And the second part is, was time born, or can you designate that as a start of the time in the universe?
Yes, correct.
Right? Okay.
Yes.
So this is an open-ended question. So I'll just give my perspective, a little more details, and leave it for you. Probably the other panelists can add value to it. So basically, the Big Bang is a prediction from gravity, from classical general relativity, and also you can have Big Bang from other theories of gravity which closely resembles Einstein's theory. Let's stick to Einstein's theory. So if you apply Einstein's theory to the universe as a whole with some assumptions of statistical isotropy and spherical symmetry, or you can even relax these assumptions sometimes. But if you do that, you find that the universe is, one of the solutions is that the universe is expanding. The scale factor is what decides the length scales in the expanding universe. And we see that the scale factor is increasing with time. So if you trace back in time, you will approach a point where the scale factor was 0. And this is what mathematically people refer to as Big Bang. But however, we should keep in mind that this is a classical theory. And the classical theory is not expected to hold very close to the points where the scale factor is 0, which means the universe was very small in volume. So the classical theory would break down, and the real physics should be investigated using quantum theory. So although most of the things in the Big Bang theory of cosmology is consistent with observations to some extent, the very idea of the explosion in the beginning or the singularity in the beginning is not correct. It's a limitation of the classical theory. And whether or not time was born there, nobody knows. There are scenarios of bouncing cosmologies where the universe did not have a starting point literally, but the universe expanded from a very small volume to what it is today. And if you go behind that point in time where the universe was smallest in volume, you would find another universe just like our own, and this can keep on going in cycles. So this is one idea of bouncing cosmology. So there are various scenarios, and it's an open-ended question. We don't know if time started at that point. Yeah, that would be my answer. Thank you.
Right. Yeah, great answer. Thank you. We will take a last question, which is asked by Arya Shrimal. It is, what are quasars? Ruchika, could you please answer this question?
Okay. So quasars are central black holes which are accreting very very efficiently. So uh, they are basically active galactic nucleus, but they are different from what we see in the local universe. So quasars are basically only seen in high redshift universe, which is not the local universe. We know more C quasars, or there are very very few cases. um, so um, so the thing is that their optical spectra shows, if you look at the photons in the optical spectra, you will see very broad emission lines which are associated with the quasars. And well, they're very shiny objects, and they are highly accreting objects. uh, yeah. um, and sometimes they have radio jets associated with them, but not all quasars. But you can say that their accretion efficiency, or the black hole which is accreting the material, uh, that's very very high. The rate of conversion of the matter it is sucking in, and the output radiation it is giving is very high. So
Right. And so, in addition to this, like Yash or Vaishak, would you like to add something to this?
The defining feature of a quasar is like its brightness in optical, and it's like it's basically one point in a galaxy which is so far away, and it is it's basically outshining every other galaxy. That's why, like, the activeness of the central black hole is the main defining feature of a quasar, which makes it such an interesting object. Like, basically, it's one point in the sky which is so bright that its light is reaching us, and it's so far away that we cannot even comprehend that. It's like it's that like that distant object can lights reach is reaching us. So it's like it's a very interesting object in that sense.
yeah. So I'll just
Yeah, yeah.
add one more point, that it's basically the merging galaxies which host such quasars, because it needs a very high fuel supply, the coal gas supply, to have a quasar. And so that you will find mostly in the epoch of redshift, between redshift of 2 and 3, where such high activity of fueling was going on. That's also the epoch when the most of the galaxies were forming stars. So
Right. Okay, so thank you so much for answering these questions, and we have come to the end of the session. We like there are a lot of live questions yet, and we are running out of time. And we there are a lot of questions about black holes. So, but then nothing to worry. We have tremendously exciting special talks coming up in the evening. My colleague Sonal will shortly announce these details to you. So over to you, Sonal. Sonal?
Ankit, if I may add a line at the
Oh
end
yeah, please.
before Sonal takes over. Yeah.
Yes. Please
So
add.
all these questions were wonderful, and as you saw, most of them were open-ended. And I mean, if you have your own ideas and theories of what happens at the beginning of universe, what happens inside of black holes, we would all urge you to take up research and find
Oh
answers to
yes,
these.
yes.
Yeah. So
Any more final thoughts, Siddharth?
I mean, just to add to what Vashaka said, these are all interesting questions that have been. These are interesting questions. These are very basic questions at the heart of astronomy, right?
True.
In general, I mean, it's a short session that we had, but if anyone wants to know in more detail, like what do astronomers do, or have more questions, then I think most of us are very okay with people contacting us over email and sending us their questions. So
Yes.
feel free to do that, and we'll try our best to answer your questions if you send them through emails. Yeah.
Right. So yes. Right.
Questions come to can come to SciPop, IUCAA Science Outreach, and
yes. So
then it can come
Sonal
back to
is
us.
about to make those announcements. So thank you so much for joining, for your time, and for answering all the questions. Sonal is about to make a very important announcements regarding the special and very exciting talks this evening, which are going to happen this evening. Over to you, Sonal.
Thank you, Ankit, and thank you very much, yes, Siddharth, Ruchika, and Vaishak. It was a wonderful session, and I am sure that our viewers are very happy that you have answered their questions so nicely, and you have also raised an interest uh, in the field of astronomy and astrophysics. So, thank you very much once again. And as Ankit said, we are going to have some wonderful sessions lined up now. So at 6:30, there is going to be a conversation with Nobel laureate, uh, Professor Rainer Weiss, uh, on LIGO India YouTube channel. The link you can find in the description. As well, after the talk, we are going to have a live sky watching session. So it will start at 7:30, where we are going to look at the planets through a telescope. Of course, it will be a live session, and it will happen on this channel only. As Siddharth and others mentioned, please feel free to drop any questions if you have related to astronomy, astrophysics, and regarding careers to our email ID, scipop@gmail.com. Thank you very much. And with this, I would like to end this session for a short break of an hour, and hope to see you all in the evening sessions. Thank you very much.
Thank you so much. Bye.
Thank you.